Welcome to today's Explainer. We're about to dive deep into one of the most volatile, yet absolutely brilliantly designed chemical factories in the known universe. I'm talking about your own body, specifically the pancreas. You know, most people just think of the pancreas as that organ that makes insulin, but it hides a much darker, way more dangerous secret. Deep inside, it's constantly manufacturing literal biological explosives. Let's get into it.
So think about this. It's a really profound biological paradox. When you eat a heavy meal, let's say something super rich with tough proteins and heavy fats, your pancreas starts pumping out enzymes powerful enough to completely liquefy that food. So if it can dissolve a tough piece of meat right there in your digestive tract, why doesn't it dissolve its own tissue? How on earth does it survive its own firepower? Well, today we're going to uncover the brilliant biological failsafe that actually keeps you from digesting yourself from the inside out. And it all comes down to a little master key called trypsinogen.
Section 1. The digestive power plant. To understand exactly where these dangerous chemicals are housed, we first got to look at the sheer scale of this system. The pancreas actually has a dual identity. The endocrine system is the one you hear about all the time, right? That's the side responsible for secreting hormones like insulin directly into your bloodstream to regulate your blood sugar. But we're focusing on the other side today, the exocrine system. This is the heavy-duty digestive power plant. Every single day, it synthesizes, packages, and secretes about 1.5 liters of highly alkaline digestive juice and enzymes straight into your duodenum, which is the very first part of your small intestine.
Now, this incredible labor is strictly divided. First up, you have the acinus, which is made up of acinar cells. You can think of these as the biological munitions factories. This is where the explosive enzymes are actually synthesized and packed into a really low-volume solution. Then you have the ductal cells. These basically act as the cleanup crew. They produce this massive wave of water and bicarbonate to physically flush those enzymes out and carry them safely down to the duodenum.
Section 2. The autodigestion paradox.
Okay, so we've got the factory and we've got the flushing system, but just look at the sheer destructive firepower produced in those tiny acinar cells. Your pancreas makes a staggering variety of enzymes to handle basically whatever you throw at it. You've got amylase to hydrolyze heavy starches, like the carbs in gari, fufu, or yam. You have pancreatic lipase, which binds to dietary fat droplets to break down triglycerides, like palm oil. You even have nucleases, which literally break down the DNA and RNA present in your food. I mean, these chemicals are absolutely phenomenal at their job. But remember, human tissue is also made of proteins, fats, and nucleic acids. If these enzymes were let loose inside the pancreas, the destruction would be catastrophic.
Section 3. Trypsinogen, the master key.
So how exactly does the body handle these biological explosives? Well, it uses an incredibly elegant biological safety pin. These dangerous enzymes are almost never stored in their active form. Instead, the pancreas creates what we call zymogens. A zymogen is basically an inactive proenzyme. The acinar cells package these zymogens up like grenades with the pin still firmly left in place. Because they're inactive, they can be safely stored right there in the pancreatic tissue without causing any damage whatsoever. They're completely harmless as long as they stay inside the organ.
This all builds into a brilliant activation sequence. Trypsinogen is our central inactive zymogen here. Step 1, it leaves the pancreas and safely enters the duodenum. It's only here, completely safely outside the organ, that step 2 happens. A special enzyme on the intestinal wall called Enteropeptidase cleaves the trypsinogen, converting it, in step 3, into active trypsin. Now step 4 is where the magic really happens. Active trypsin acts as this autocatalytic master key. It starts waking up all the other trypsinogen molecules and it unlocks all the other inactive zymogens, like chymotrypsinogen, turning them into their fully active protein-destroying forms. The explosion is safely contained out in the intestine, exactly where your food is.
This is an absolutely vital takeaway for us. The entire cascade of protein digestion depends strictly on this one single master key. If trypsinogen is biochemically blocked, or if it just isn't activated by that specific intestinal enzyme we just talked about, all the rest of the zymogens stay fast asleep. You would completely halt the digestion of heavy proteins like beef or fish. That's how absolute this failsafe is.
Section 4. Flushing the system safely.
But you know, just having safe inactive enzymes really isn't enough to prevent a disaster. The body still has to get them out, and quickly. When acidic and fatty chyme leaves your stomach and enters the small intestine, it triggers 2 primary hormones. First, secretin is released, which tells the ductal cells to produce a massive volume of alkaline fluid. Second, CCK, or cholecystokinin, is released, which tells those acinar cells to dump all those inactive zymogens we just went over. This dual pathway perfectly times out a massive flush of enzymes and fluid right at the exact moment the food arrives.
The chemistry of that flush is honestly fascinating. At rest, the pancreas just trickles out a low bicarbonate fluid, but the very moment you start actively feeding and secretin gets released, the ductal system dramatically shifts gears. It moves into this highly active, high-flow state, pumping out massive amounts of bicarbonate while simultaneously dropping its chloride levels. Why does that matter? Because that high bicarbonate fluid does two crucial things. It neutralizes that highly acidic stomach acid to a perfectly safe pH of 8.0, and it creates a literal tidal wave that rapidly sweeps those inactive zymogens far away from the delicate pancreatic tissue.
Section 5. When the safety fails.
So as you can see, it's a perfectly balanced system. But what actually happens when the safety fails? This timeline traces a pretty terrifying medical reality. Step 1, the outflow of the pancreas gets blocked, which happens very commonly by a gallstone just getting stuck in the duct. Step 2, that high-pressure flushing system we just talked about, well, it's still trying to work, but it has literally nowhere to go. So enzymes accumulate and tissue pressure violently rises. Step 3, this intense pressure and local cellular injury cause the failsafe to break. Trypsinogen gets prematurely activated into trypsin while it's still sitting inside the pancreas. And finally, step 4, the master key has been turned in the exact wrong room. Trypsin unlocks all those other zymogens and uncontrolled autodigestion begins.
The consequences of this are just blunt and brutal. When the pancreas literally digests itself, it results in acute hemorrhagic pancreatitis. The activated enzymes destroy the organ's tissue, they liquefy the surrounding fat, and they trigger a massive systemic inflammatory response. It causes severe, excruciating abdominal pain, and honestly, it can be life-threatening. It's the ultimate proof of why the trypsinogen safety mechanism and the rapid flushing of the ducts is absolutely vital to your survival. The systems inside you are constantly balancing immense destructive power with breathtaking elegance. Next time you sit down to enjoy a heavy, really rich meal, just take a second to appreciate the complex biophysics happening inside of you. Think about those zymogens waiting so patiently, that massive bicarbonate flush, and the master key of trypsinogen keeping you entirely safe. Just ask yourself, how many biological explosions did your pancreas safely disarm today? It's pretty amazing to think about. Thanks for joining me for today's explainer, and I'll catch you next time.